So good morning or good afternoon, ladies and gentlemen. I'm very grateful for being here. I especially want to thank Jerry and all organizers of this wonderful, nice, motivating, inspiring, and vitalizing meeting. I'm enjoying a lot. And I want to thank you also for being here now until the end, listening to my talk. So my name is Cecilia Mendive. I'm from the Department of Chemistry from the National University of Mar del Plata, Argentina. And my talk will be about the role of water in the photoinduced deaggregation mechanism of titanium dioxide nanoparticles. So I will just tell you a little bit more what I already published in the poster here in the conference. Titanium dioxide is the material that we work with because it's an excellent photocatalyst, and it finds many applications, for example, in environmental remediation to clean or decontaminate water or air, in technology with self-cleaning materials or anti-fogging surfaces, using the superhydrophilicity property that it has, as well as disinfection, and also in energy, because using titanium dioxide and solar light or UV light, one can produce hydrogen by water splitting. Today we have heard a nice talk about water splitting, but this way is really clean. And titanium dioxide has many potentials, and it's very promising for environment. So the principle of photocatalysis is basically, as I explained to you last time very briefly, if this is the particle of titanium dioxide, as it is a semiconductor, it has a forbidden band for electrons. There's a band gap. And upon absorption of a photon, one electron is promoted from the valence band to the conduction band, and in that moment, an electron-hole pair is generated. If the electron is picked up by an acceptor, then the hole can oxidize, for example, a pollutant, into a full mineralization state, and this reaction will depend on which the pollutant is. So how to study these systems? As long as all these reactions happen at the surface of the particles, we use this technique, which is, as far as we know, the only one that we can use to study the surface of a photocatalyst in contact with the water solution. This is the attenuated total reflection device in the IR spectroscopy. This is just putting a zinc selenide crystal in the optical path of the beam, and when the light enters, it's totally reflected up and down until it goes out and goes to the detector, and in every reflection, there's an evanescent wave that takes information on what you put on the top of the crystal. So here we place a layer, I prepare a layer of titanium dioxide nanoparticles, a very thin layer between 1.5 to 1.7 micrometers, in contact with the water solution I want to study. In that way, I take information of the adsorbed species, for example. This is what I'm interested in. And I can also put a lamp on top of it and monitor the photocatalytic reactions performing in this moment. So doing all these things, we found very interesting results that we didn't expect. For example, oxalic acid is it's the simplest decarboxylic acid, adsorbed at the surface of titanium dioxide in contact with water solutions. We saw that in the dark, the spectra was this, and after 8 hours of illumination, the spectra of adsorbed oxalic acid was increasing. Not the dissolved amount of oxalic acid, otherwise it was not going to be mineralized. But the adsorbed species, yes. So as you see the integrated total spectral area, you see in the dark it reaches somehow the equilibrium, and then when one switches on the light, the integrated area increases. And a very funny way of studying that is making periods of dark and light intermittently, and one sees that under light there's always a positive slope indicating that there's more oxalic acid adsorbed at the surface, while this doesn't happen in the dark. So then, oops. we remove oxalic acid and study water in contact with titanium dioxide. If one takes a spectra along 24 hours, there's almost no change. But after only 8 hours of illumination, one sees that the spectra change considerably, and especially in this area where there's a bending mode of water, indicating that water enters in the system within the path of this evanescent wave that is probing my system. This is the bending mode of water I showed before, which increases with time. The bending mode of water would indicate that there's either free water or adsorbed water as in a molecular fashion, or dissociatively at the surface. In order to estimate the quantity of water that enters into the system, we have modeled our layer, assuming that it can grow only in the z direction, since x and y is fixed by the holder, and assuming that it grows only because water enters within the layer that we prepared. We also observed that the particles do not swim away, stay there, it's simply thicker. And taking into consideration that the evanescent wave also depends on the amount of titanium dioxide and the thickness of the layer, and going through the mathematics of this, I don't know why it disappeared. It was not a trick. Oops, there. So going through all the mathematics, we see that the volume that entered into my system after 8 hours of illumination was around 0.15 milliliters, which for that system would mean 18% more volume. So it's quite a lot of more water entering the system. And this would mean, in principle, that the particles separate each other in order to elongate this axis and make the volume bigger. Then we started thinking, well, something is going on with the particles, why they separate each other, what is, this is something only a property belonging to the layers, or maybe we find this phenomenon also in suspension. So we tried to study suspensions as well, and we found the same. These are aqueous suspensions of titanium dioxide, and if one performs the adsorption curve, in this case is fluoride, but we have done it with many anions and with many organic molecules, one sees that the adsorption curve after illumination is always higher, indicating that there are many more adsorption sites after illumination. A very simple test also to see that the agglomerates, the naturally occurring agglomerates in the system may break and expose more surface is a centrifugation. These are two photos. In both cases, these are different titanium dioxide materials of different particle sizes. These are two photos of the same suspension in the dark and under illumination. So in the dark, if you centrifuge, you will see that there's a sedimentation of practically everything, but under the same conditions, and after 2 hours only of illumination, the suspension remains suspended, indicating as well that something like this would happen. Agglomerates may break, leading to smaller agglomerates that can stay longer suspended. And this is what we call the photoinduced deaggregation mechanism. But what's the reason for this? And that's a big question. At the beginning, we thought that it had to be related only to the energy released when there's an electron-hole recombination, because this is a process that happened the most. This is an undesired process for photocatalysis. One wants that these two species really react, and they do not recombine, but they recombine a lot. And we thought, okay, there must be a lot of energy released that the system can use to put apart the particles. But we found that some people made very careful thermodynamic measurements, and they found very low values of energy, maybe on the order of 1 hydrogen bond per mole of titanium dioxide. This would be more or less in the order of I said, of one hydrogen bond. So this would mean that the particles maybe are very weakly attached, and they should be very easily broken or teared apart. But this is not the case. If you see the agglomerates, you will see that the particles are really very strongly attached. Many times they are attached. Oh yes, thank you. I have the mouse very dry. Many times you see that the particles are topotactically attached. That means that they align their crystallographic planes, and these are very strong attachments. So we think that, yes, some energy may be released, and this could trigger another reaction or another phenomenon that helps finally these strongly attached particles to deattach. And we think that the water plays a very important role. If this is a cluster, these are simulations that we also made in our labs. This is a cluster, and the cluster of titanium dioxide firstly is hydrated by a first layer, molecularly or dissociatively adsorbing at it, and then by stacking layers of water, probably in one moment, we think that all these layers may organize themselves in a way that they can produce a structured system, perhaps similar to a crystal water, knowing that crystallization is an exothermic reaction of around 6 kilojoules per mole. We think that perhaps this organization and this structuring of water is also an exothermic reaction, contributing as well to the system. And in that moment, so two particles experimenting such an energy input may start separating, and then when water tries to build up again on this freshly open surface, finally they separate. So that's the main important role of water we think we have in our systems, combined also with the recombination energy released. So in summary, because I don't want that you are very hungry because of me, I wanted to tell you that the disaggregation of agglomerates under UV illumination is observed not only in layers, but in suspensions, that the deattachment of nanoparticles shall be described not only from a thermodynamic point of view, but also considering the crystal buildup of water at the surface wedging into the spacing between both particles. These are open questions that now we are dealing with, and we think that we ask ourselves whether this occurs in the presence of other liquids, for example, or if this process is reversible upon turning to dark conditions, and why the particles do not swim away. Is it related to the structuring of water? And okay, so we are all welcome to come to Mar del Plata. I hope you find a moment to visit us. We will like to receive you, and I have to thank to all these people that, thanks to them, all this work and more also has been done. As you see, Mar del Plata is a touristic city at the sea, and it's far away from Buenos Aires, not so far away from Buenos Aires, but you can easily reach. And thank you very much for your attention. Here you will find us.
Thank you very much. Do we have a single question for the poster? Yeah, that's one down there.
Instead of the particle separation, have you looked at maybe the stretch bonds and done a Raman spectra of them to see if there's any change in them?
If we see any change in the spectra upon?
The Raman spectra of the stretch bond?
Well, actually, this is a process that has a lifetime of around 1 or 2 picoseconds. So unfortunately, we cannot,
okay, yeah,
yes, we cannot measure it with our method.